So in the previous videos, we've talked about vector form of a line, and we've talked about parametric form of a line. And then there's another form of a line that you guys have known about all along, right? This thing that's going to be called Cartesian form of a line, which is basically just any form of a line that involves x and y in a traditional sense. So it's basically just taking one of these vector form or parametric form lines and putting it in point slope form or standard form or slope intercept form, anything you guys are used to seeing from algebra. On the SL test that most of you are taking, this is only done in 2 dimensions. We don't do it in 3-dimensional space. You can, but we're not going to do it. Okay. So down below, I sort of have these two forms, right? We've got vector form on the left, which hopefully you remember has a basically the position vector of a point on the line, and then it has the slope. I'm sorry, not the slope, but the directional vector of the line. And what I want you to recognize is when you go to point slope form, it's really easy because this thing here is effectively a point, and this thing here is effectively a direction. The catch is that the top direction is an x value, in other words, it's your run, and the bottom is a y value, which is effectively the rise. Like if you think about it, if you think about the vector like 3, 5, 3, 5 means over 3, 1, 2, 3, and up 5. That was ugly, but the idea is that direction effectively has a rise of 5 and a run of 3, right? And so if you're going to point slope form, it just means take that directional vector, flip it upside down, and write it as a slope. Take the point that you have and use the y and x coordinates, and you're effectively done. You've taken the vector form and put it in point slope form. We can also go back the other direction by doing sort of the same things in reverse, right? The big thing here to remember is that the directional vector gets flipped over when we write it as a slope because a vector has x on top and y on the bottom, whereas a directional vector has y on top and x on the bottom. So, sort of, to make this specific, if you're converting from vector form into Cartesian form, we're basically going to use point slope form, which is the thing I was just talking about, right? You'll take the directional vector, rewrite it upside down. You'll take the position vector and use it as the point. Okay. So as an example, write the line given in vector form below in the form ax plus by equals c. Some people get tripped up because they look at this and they say, oh no, that's not point slope form. That's okay. Just take this line. We are going to write it in point slope form. And once we're in point slope form, then we'll put it into this, I guess we call it standard form. So it may be helpful for you to first rewrite this line so you can actually see it in vector form, right? So vector form means there's a position vector, a point on the line, plus time times the directional vector. So, pause the video for a minute or make sure you at least have this in mind mentally. Your position vector for the point on the line should be 3, -5. Your directional vector should be -1, 2. I got those from here for this one and here for this one. Okay, so to me, that means that we have a point at 3, -5, and it means that we have a slope of 2 over -1. I'm getting those from here. I'm just turning it upside down. And so I might as well simplify that. The slope is really -2. So now that I have that information, I can use point slope form. I can write y plus 5 equals -2 times x minus 3. And now all I have to do is change this into ax plus by equals c form, right? In other words, distribute things and move them around, right? So y plus 5 equals -2x plus 6. If I move the 2x this way and the 5 this way, I'll end up with 2x plus y equals 1. And that is sort of my Cartesian form. That's my standard form of this vector form line that was given in the beginning. So note, my process was basically first go to point slope form, then once I was in point slope form, I converted into this standard form. Okay. Now to go the other direction, if you want to convert from Cartesian form back to vector form, I think the easiest way to do it is to take that Cartesian form and put it into slope-intercept form. And slope-intercept form, if you forgot, is y equals mx plus b. The reason I think this is easy is that once you have it in this form, you can already see the slope, and you actually also have a point. This y-intercept b is a point. It's the point 0, b. So if you can get it to y equals mx plus b form, you've got the pieces you need, and we just have to write it in vector form. Right? So if we start with 3x minus 4y equals, I'm sorry, not equals, but 3x minus 4y plus 12 equals 0, we can start rearranging this. This is negative 4y equals negative 3x minus 12. That means y is 3/4 x plus 3. So now that I'm looking at this thing in this form, I can tell that my slope is 3/4 and my point is 0, 3. So now if I want to take this and convert to vector form, I just have to see this slope as a directional vector and this point as a position vector. Right? Pause the video for a minute and think about what is the directional vector going to be that you get from a slope of 3/4. Should be 4/3. I'm sorry, 4 and 3. The point we just write as a position vector 0, 3, and once you have those things, we can just write the vector form of the line. Vector form of the line will be r equals 0, 3, that's the point on the line, plus t times my directional vector, which is 4, 3, just sort of the upside down version of the original slope. And there it is. In some sense, those are the basic problems for converting the two directions. One other thing they'll do is they may start talking about parallel lines and perpendicular lines, and I think that's what my next example is about. Yep, here we go. So write the equation of a line in vector form, which is perpendicular to the line given below and passes through the point 5, -7. Alright, so what I really want to focus on here is this idea of perpendicular. And there are two ways of approaching this. One of them is by thinking about the dot product, and the other is thinking about what you guys already know. Right? Like when I see this line here, I see this as being the direction. Right? And if that's the direction, what slope is the same as that direction? The slope that has that same direction is the slope 1 over -3. Right? So when somebody says, oh, the direction of this line is, the vector -3, 1, the slope is basically -1/3. But now, we want to have a line that's perpendicular to this one. So if I asked you, what is the slope which is perpendicular to that one, I suspect that everybody would sort of respond that, well, it would be the opposite reciprocal of that slope. So it would basically be positive 3 over 1, in other words, 3. And so now if you have that slope, what direction, in other words, what directional vector would we write that has a slope that's the same as a slope of 3? Well, we have to take this idea of 3 and write it as a directional vector. Right? And the way that we do that, remember, is sort of by turning it upside down again. Right? So this is going to be 1 and 3. Now, I worry that I may have lost somebody there, so I'm going to go back through that again. Remember, how do we change from direction to slope? We do that by taking the directional vector and turning it upside down. So -3 and 1 turned into 1 and -3. Then we made it perpendicular. We sort of flipped it over again and changed the sign. And that gave us 3. Note that 3 is really 3 over 1. Then, when I went from that slope back to the direction again, I take this 3 over 1 and I change it into 1 over 3. I'm sort of flipping it back over again. So now, they wanted me to give a line that's perpendicular, so I put t in front of the directional vector. Now I just need a point that's on this perpendicular line. Well, they told us that it's supposed to pass through the point 5, -7. So I'll put 5, -7 as a position vector. And here is this line, which is perpendicular to the original one. And this is your answer. You're done. I mean, like, as simple as that. I suppose there's another alternative way of thinking about perpendicular vectors. I guess I'll use a green color for this. If we have the vector AB, how can we find another vector that's perpendicular? Well, the idea is, in some sense, you could just flip them over and make one of them negative, right? It's sort of the same idea as taking a slope and flipping it over and making it negative. I'm just switching these around and making one of them negative. You'll notice that the dot product here is 0. If you did AB plus -AB, you'd end up with 0. So anyway, that's a quick thought about that. So now I have one more example for you, and I'm hoping you guys will be willing to try this one on your own. For this one, write the vector form of equation of a line that passes through that point and is perpendicular to that line. If you need a hint, I'll give you one here. Otherwise, pause the video and try it on your own. So my hint is going to be, if you want a vector form equation, it means that you need a position vector of a point, and you need a direction vector. So think about where you're going to get those two things from, and then go about finding those things. So the position vector should be really easy. They told us that the line was supposed to pass through 11, 8, which means my position vector is going to be 11, 8. Now my directional vector, what I know is that it is supposed to be perpendicular to this line. So my thought is that I need to find the slope of that line. So if I have 5x plus 3y equals 13, that means 3y is negative 5x plus 13. That means y is negative 5/3 x plus 13/3. To be honest, I don't really care about the 13/3. What I care about is that the slope is negative 5/3. So that's the slope of the line. I need to know what the slope is that's perpendicular to that. Well, a perpendicular slope is simply the opposite reciprocal. So the perpendicular slope would be 3/5. Now I have to take that slope and change it back into a directional vector. So what is 3/5 as a directional vector? Well, we flip it back over. I get 5 and 3. I now have my position vector and my position vector for the point and my directional vector, so we can write the equation of the line. My line will be 11, 8 plus t times 5, 3. And we're done.